Assalamu alaikum everyone. In this lecture we are going to talk about the complex power flow in the transmission lines. In the last lecture we studied about the surge impedance loading, and if I have to define the surge impedance loading, so the surge impedance loading is the loading corresponding to the surge impedance, and the surge impedance is actually the characteristic impedance of a lossless line. So this we covered in the last lecture, and after that we derived the formula for the surge impedance loading, and we also explained the Ferranti effect. So this Ferranti effect actually happens when the transmission line is lightly loaded or there is no load attached at the receiving end. And what happens that the receiving end voltage actually becomes greater than the sending end voltage. So VR is greater than Vs. So this is your receiving end voltage and this is your sending end voltage. So if we have a lightly loaded transmission line or there is no load attached at the receiving end, then the Ferranti effect will occur and the receiving end voltage will increase and will be greater than the sending end voltage. And after that we solved an example related to the traveling waves and also for the long transmission line which is lossless. Now in today's topic we are going to cover the complex power flow in the transmission line, and we will be finding the receiving end power, receiving end complex power, and we will also be calculating the sending end complex power, and lastly we will be covering the line compensation for the transmission lines. So starting from the receiving end complex power, so we will be considering a transmission line, and I am representing the transmission line in terms of ABCD constants. We have a sending end voltage Vs, angle delta, sending end current Is, receiving end current IR, and receiving end voltage with an angle 0. So now what I have done, I have represented the transmission line in A, B, C, D constants, and it is a generalized representation. So we can represent any transmission line in terms of ABCD constants. So it can be any of the transmission lines which can be short, medium or long transmission line. So we will be deriving the generic expressions for the receiving end and sending end complex power. So if I have to define few variables, so Vs, this is the sending end voltage, it has a magnitude and it has an angle delta, and this angle is actually the rotor angle. So rotor angle of the synchronous generator which is producing the power. Then we have a receiving end voltage Vr, again it has a magnitude and the angle is 0 degree. For the constants we have again magnitude and it also has a angle theta A. So this is your constant A. For constant B we have magnitude and angle theta D. Similarly we can also write it for the constants C and D. Now what we have to find is the receiving end complex power, and the complex power is S, and for the receiving end I have used R, and it has two parts, real part, real power, and reactive power. And the final formula is 3VR IR conjugate. So this is the three-phase power, because the receiving end voltage is considered to be the phase voltage. So that's why I have used 3. If I have used the line voltage, then this 3 should be replaced by under root 3. So we know the receiving end voltage which is equal to VR angle 0, right, which is VR magnitude and angle 0, but we don't know the receiving end current, right? So if I have to calculate the receiving end current, I will use the generic equation for the sending end voltage and the sending end current, the sending end voltage is actually equal to constant A multiplied by the receiving end voltage plus constant B multiplied by the receiving end current. So this is the same equation that we have used before. So we have a sending end voltage in terms of receiving end voltage and receiving end current multiplied by the respective constants. But I have just segregated it into the magnitude and phase of the constants as well as for the voltage values. So now if I have to calculate IR from this equation, so the IR will become IR is equal to Vs angle delta minus A. So I will take this term to the other side of the equality and it will become negative angle theta A VR angle 0 divided by constant B. So this is the equation for the receiving end current. So now what we had to find was the receiving end complex power. So we already know the receiving end voltage. Now we also know the receiving end current. So now I will put this current value at the receiving end in the complex power, and the SR will become 3 VR angle Vs angle sigma minus theta B minus A VR over B angle theta A minus theta B, and we will take the conjugate of the current value. So this is conjugate. So after solving, it will become SR is equal to 3 VR Vs over B angle theta B minus delta minus 3 VR over B square angle theta B minus theta A. So this is your receiving end complex power. Now in this case, the receiving end voltage and the sending end voltage, these are the phase voltages. Now if I have to convert this into the line voltages, what I have to do, we know that V line, which is equal to under root 3 times V phase, right? So if I'll replace this in this equation, so the receiving end complex power will be in terms of line voltages, the line receiving end voltage and line sending end voltage. So it will become SR is equal to under root 3 Vs under root 3 VR divided by B angle theta B minus sigma. So what I have done, I have converted this 3 into two parts, under root 3 and under root 3. So this will become 3 when we multiply those two. And after using the same under root 3 value for the receiving end voltage, it will become angle theta B minus theta A. And the final equation for the receiving end power, it will become VSL. So this L represents the line voltage and VRL. So I'm not using these bars right now, so just assume these are the magnitudes, right? Divided by B angle theta B minus sigma minus A VRL square over B angle theta B minus theta A. So this is your complex power. So now the complex power actually has two parts. It has a real part P and a reactive part Q. So if I have to write the real part PR, it is equal to VSL VRL divided by B and cosine of theta B minus delta. Similarly for A, it will become VRL square over B cos theta B minus theta A. For the reactive power at the receiving end, it is the imaginary part of SR, right? So this was the real part, this is the imaginary part of SR, so it will become VSL VRL over B sine theta B minus delta minus A VRL square over B sine theta B minus theta A. So these are your real and reactive power for the receiving end in the transmission line. So now if I have to find the sending end sending end complex power, for the sending end complex power, again we know the formula. For the sending end, the formula will remain same. The complex power is actually the summation of real and reactive power, where reactive power is the imaginary part and the real power is the real part of the complex power, and it is 3 Vs I S conjugate. So this is your sending end voltage and sending end current, right? Again, we don't know the sending end current, so we have to calculate the sending end, and I will be using the same formula. Vs is equal to A times VR minus VIR, right? So right now I'm not using the magnitude and phase parts of all the voltages and current. Once I will solve it out, then I will replace it with the magnitude and the phases of voltages, sending end voltage, receiving end voltage, and also for the constants. So now for IS is equal to CVR plus DIR, right? This is plus. So now if I have to find IS, we don't know IR, right? So I will calculate IR from equation number A. So it will become IR is equal to Vs over B minus A over B VR. So I will put this IR value in second equation. So IS will become IS is equal to CVR plus D into Vs over B minus A over B VR. So after solving it down, it will become D over B Vs minus AD minus BC over B into VR. So now if you remember the properties of the ABCD constants, we know that AD minus BC is equal to 1 and A is equal to D. So this can be replaced by 1 and this is replaced by A. So IS will become A over B Vs minus VR over B. So this is your sending end current. So now I will replace the constants as well as the voltage values with their magnitude and phase parts. So it will become A divided by B Vs angle theta A minus theta B plus sigma minus VR over B angle minus beta. So this is your sending end current. What we have to find was the sending end complex power. So sending end complex power is actually equal to S is equal to 3 Vs Is conjugate. So now we know the value of Is, so I will use this value in the complex power, and it will become SS sending end complex power is actually equal to 3 Vs angle sigma A Vs over B angle theta B minus theta A minus sigma minus VR over B angle theta B. So now again these values Vs and VR, they are the phase voltages. Now converting it into line voltages. So we will multiply these three inside 3Vs inside the bracket, and this will become the final complex power in terms of line voltages will be A VSL square over B angle theta B minus theta A minus VSL VRL over B angle theta B plus sigma. So this is your sending end complex power. So like we have done in the receiving end complex power, we can again distribute it into two different parts, the real power and the reactive power. The real power will become PS is equal to A VSL square over B cos theta B minus theta A minus VSL VRL over B cos theta B plus sigma. So this is the real part of the complex power, and for the imaginary part, that is the reactive power of the sending end, that is A VSL square over B again sine theta B minus theta A VSL VRL over B sine theta B plus sigma. So this is your imaginary part of the complex power. So now we have calculated the generic terms for the sending end complex power as well as for the receiving end complex power. So now we want to find the maximum power transfer. For the maximum power transfer, we will use the maximum power transfer theorem or the maximum value theorem, in which we will take the derivative with respect to delta and make it equal to 0, right? So we have the formula for PS, that is this one. So now I have to calculate the maximum power for this one, so I will take derivative of this PS, this whole equation with respect to delta, and then make it equal to 0. So what I will be doing, I will be taking the derivative of real power with respect to delta and will be making it equal to 0, right? So A VSL square over B cos theta B minus theta A minus VSL VRL B cos theta B plus sigma. So now all these values, these are the magnitude A, B and VSL, and these theta B and theta A, these are the angles of the constants. So A, B cos theta B minus theta A, all these values are constant, so the derivative of this value will be equal to 0. We are left with the derivative of the second part, so that will be 0 plus VSL VRL over B sine theta B plus sigma equal to 0. Here it is equal to 0. So now if I have to calculate the value of sine theta B plus sigma, that is equal to 0, because this will go to the other side of equality, it will become 0, and theta B plus sigma will either be equal to 0 or pi, because sine inverse 0 will either be equal to 0 or pi. But in this case we will be taking the value pi, because delta can never be equal to 0, it always has some value. So the summation of two values will be at least greater than 0, so that's why I will be taking theta B plus delta will be equal to pi. So the maximum power equation, that will be PS max, right? So we got the value of theta B plus delta. If that will be equal to pi, then the equation that we have calculated for the PS, this one, if we will replace theta B plus sigma equal to pi, this will give us the maximum power value or maximum power transfer value. So now I will be replacing this value in the PS equation. So this will become A VSL square over B cos theta B minus theta A minus VS VRL over B, and this part will become cos pi, and the value of cos pi is equal to -1. So this minus will be multiplied by the minus before the part of the equation, and it will become A VSL square over B cos theta B minus theta A plus VSL VRL over B. So this is the equation for the maximum power at the sending end or maximum power transfer equation. So this is the power that can be sent from the sending end towards the receiving end. Similarly, we can also calculate the value for the maximum reactive power. So for QS max, we will have the equation that is equal to A over B VSL square sine theta B minus theta A. So this is your maximum reactive power that can be transferred. So these are the equations that we can apply to any of the transmission line if we know their constants. So just to give you a simple explanation, I will be applying these two equations to the short transmission line. So if I will be using the short transmission line, I will consider the circuit short transmission line. So the circuit of short transmission line is, there is a line impedance and we have a load across which we are getting the voltage VR, and the current at the receiving end is IR, and this is impedance. We are having a sending end current equal to IS and the voltage PS at the sending end. So this is a equivalent model of the short transmission line. We don't have any capacitance in the short transmission line, or we don't consider the capacitance because the value is too small. So this is the equivalent circuit of the short transmission line. Now we are considering it to be lossless, right? So if it is lossless, then G is equal to 0 and R is equal to 0. So if R is equal to 0, then the impedance only has the inductive reactance part, right? So this is equal to JX. Now if you remember the constants of the short transmission line, so constant values, so it will be A, B, C and D. They are equal to 1, 0, JX and 1, and this value is actually equal to 0 because we are neglecting the capacitance in the short transmission line. So now if I have to update the sending end power equation, that will become A VSL, I'm just writing the equation again, cos theta B minus theta A minus VSL VRL over B cos theta B plus sigma, right? So this is your sending end power equation. That is the generic one that can be used for any of the transmission lines. So now if I have to find the values of A magnitude, B magnitude, theta A and theta B, we can calculate it from here. So the A magnitude is actually equal to 1 and theta is equal to 0 because it is equal to 1, and this is JX. So for B, it is equal to, magnitude is equal to X and theta B is equal to 90 degree because this J, the angle is 90 degree. So now I'll replace these two values in the power equation. So it will become PS is equal to VSL square over X cos 90 minus 0 degree minus VSL VRL over X cos 90 plus sigma. So this part of the equation, cos 90 plus sigma, this will become minus sine sigma, right? And after solving that, it will become PS is equal to Vs VRL over X sine sigma, because this will become 0. Cos 90 is equal to 0. So this whole term will become equal to 0. The second term we only have minus sine sigma. This minus will be multiplied with the negative sign before this term. The equation for the sending end power for the short transmission line will be PS is equal to VSL, which is the sending end line voltage, receiving end line voltage, reactance of the line, sine delta, where delta is actually equal to rotor angle. So now if I have to maximize this power, so I can only control this delta. So if delta is equal to 90 degree, we will have the maximum power, right? So PS max is equal to V sending end voltage, V receiving end voltage magnitude divided by the reactance of the line, and sine delta will be equal to 1, because delta is equal to 90, sine 90 is equal to 1. And similarly, this is your sending end power. Similarly, we can calculate the sending end reactive power, and that will be Vs over X, Vs minus Vr cos sigma. So now we have two equations, one for the sending end power and one for the sending end reactive power. This is the real power and this is the reactive power. Now looking at these equations, we can say that the sending end real power, it is actually dependent on the rotor angle. So if the rotor angle is made equal to 90, it will become maximum, or if it is changing, the sending end power will be changing. But for the sending end reactive power, it is dependent on the voltage difference of sending end voltage and receiving end voltage. And this delta value, it is actually small. So delta value is small. So if delta value is small, so the cos delta value will be closer to 1. So it is not very much dependent on the changing rotor angle. So the reactive power from the sending end, it is actually dependent on the difference of voltage between the sending end and the receiving end. So this was the first topic of this lecture. And what we have covered, we started from the receiving end complex power, and we used the simple equations for the sending end, sending end voltage and sending end currents that are in terms of the transmission line constants and receiving end voltage and receiving end current. From there, we calculated the generic expressions for the real and reactive power for the receiving end, as well as we also calculated the sending end complex power. And in that we also calculated the real and reactive power for the sending end, which are the generic equations, and that can be used for any of the transmission lines, medium, short or long transmission line. Then I have applied those equations on the short transmission line. We have used the ABCD constants, and we calculated the equations for the sending end real power and the sending end reactive power. And we found out that the sending end real power is actually depending on the rotor angle of the synchronous generator, and the reactive power from the sending end, it is dependent on the difference of the voltage between the sending and receiving end.